All right. Okay, so welcome everyone, and just quickly to give you the objectives of this webinar is to discuss exam techniques, to show you how to approach a question, revise some key statistical concepts and answering any questions you have. I'm not going to teach any new skills. Everything that I will discuss is part of your syllabus, and I'm assuming that you have already studied it, so we can just revise it rather than teaching it. And the seminar, this webinar is recorded. And just very briefly, in terms of kind of tips, this is a quantitative course, so you should always show you're working. Don't simply give the answer. Give all the steps and give any assumptions you make so that you can get partial credit if you have made a mistake. It's very important to execute good time management, so don't spend too much time on any given question. Try to allocate your time depending on the marks that each sub-question has. So I'm going to use the 2018 past paper, Zone A, and perhaps have a couple of more sub-questions as an extra. I'll try to cover as much as possible. Now, the difference between Stats 1 and Stats 2 paper is that in this one, in Statistics 2, you do not have any option with regards to what questions to answer. So you have to answer all the questions given. The first section are kind of shorter questions that have many parts. So yeah, you just need to, again, use time wisely so that you don't spend too much on small questions. So I'll start with the first exercise, where you have you have a list of five questions where you need to answer whether the statement is a true or false, but you need to justify your answer. Okay, so things you should use in this type of question is try to stick to definitions and properties. Okay, definitions and properties will be will allow you to give short and to the point answers. And also, I would like to emphasize the fact that you should pay attention to whether an inequality is strict inequality or kind of you have less than or equal type of situations. Okay, so I'll kind of quickly go through these five questions. You have a total of 10 marks. So the first one is if A and B are independent. Okay, so let's start with that definition again. A and B independent means that the probability of the intersection is equal to the product of the two probabilities. Okay, so this is the definition. Then we need to check whether a given statement is correct. Okay, so that statement is if I start with the kind of right-hand side, where you have the probability of the union of two events. So this is the property of the summation of two events. By kind of this property is the probability of A plus probability of B minus the probability of the intersection. Okay, so that intersection, due to the property of independence, I'll just quickly write it here, is the product of the two. Okay, since A independent of B. And then another thing that is given that I haven't yet highlighted is the fact that these probabilities are strictly positive. Okay, so they cannot be zero, which means that if we, let's say, this means that this term is strictly positive. Okay, so this term is strictly positive, which means that if I if I subtract a strictly positive term from a summation, the result is bigger than the original summation. So that will be PA plus PB. Okay, if we delete that third term. Okay, so that is it. And because we have strict inequality there, that concludes that the statement is true. Okay, so you need to write the final conclusion after you have done whatever work you're doing. Okay, so this is a true statement, and this is the reasoning, the justification. Okay, so in the second part of this question, you're given two conditional probabilities, and you need to check whether if that first statement is true, whether A and B are independent. Okay, so let's start with the definition. So I'll just write it as definition of the conditional probability. Okay, so so basically this is the statement. Okay, and then expanding the conditional probabilities will give us the probability of A intersection B over the probability of B on one side, and probability of A intersection B complement over the probability of B complement on the other side. And then if we apply cross multiplication, then we end up with probability of A intersection B times, I'm going to substitute the B complement with 1 minus probability of B. Okay, so this is the one side. And then on the other side, we have probability of A intersection B complement times probability of B. Okay, and the next step is to try to rearrange this term. Okay, so this term can be expressed as the probability of A minus probability of A intersection B. Okay, and it's easy to see that, just to kind of verify that this is the case, by drawing a Venn diagram. So you have this case, and probability of like A intersection B complement is this area. Okay, this is the A intersection B complement, which is equivalent to taking all of A and subtracting this bit. Okay, so by substituting, by making that kind of substitution, we end up with A intersection B minus A intersection B times probability of B. Okay, so I'm just expanding, so I'm kind of working through this term. And then this is equal to probability of A times probability of B minus probability of A intersection B times probability of B. Okay, so things that cancel out are these two, and then what we're left with is that this probability of the intersection of A and B is equal to the probability of the product of the two events, and that that kind of concludes that A and B are independent. And so statement is true. Yeah, yes, so statement is true. Right, so we kind of proved the first two bits. Now, very quickly, I'm going to go through the third, which is this one. If A and B are disjoint event, then A complement and be complement or disjoint. Now, when you have to prove that something is false, a statement is false, you can use a counter argument, counter example to prove a false statement. Okay, you can only use example to prove something is false. Okay, so that counterexample, okay, so let's start with the definition that A and B are disjoint, which means that the probability of their intersection is 0. Okay, so that set is empty. And so if you, but that kind of on a Venn diagram shows us A kind of B. Okay. So it's easy to see that if you have A and B, like disjoint, then the intersection, the complement of A will be all this, and the complement of B will be all this. Okay, so you get the sense that the argument is that statement is false. However, the Venn diagram is not enough to prove it. You can use a counter example, and for instance, what we can say is that if you have a sample space where you have the 1, 2, 3, 4, 5, 6, and if you have A 1 and B equals 2, then A complement will be like 2, 3, 4, 5, 6, and B complement will be 1, 3, 4, 5, 6. So the statement that A, what's it called? A intersection, A complement intersection, B complement is not the empty set. Okay, so this is a counter argument. The fourth statement here about SNT, if SNT are unbiased estimators of parameter theta, then the product will also be unbiased of theta hat. This is the definition of the unbiased. Okay, so unbiased means that E of t equals theta and expected value of f equals theta. However, expected value of the product of two random variables is not equal to the expected value of t times the expected value of s. Okay, so this is generally not true unless t and s are independent. In this case, there is no such statement, so we generally say that this is the statement is false. Okay, and finally, for the last bit, the power of the test is the probability that the alternative hypothesis is false. Well, we are going to stick to the definition in order to prove this. Okay, so by definition, we use the definition of the power. We have that the power is the probability of rejecting the null hypothesis when the alternative is true. Okay, so based on this definition, statement is false. Thus, statement is false. Okay, so this is kind of how you like the approach you should take in answering the first 5 small questions to get these 10 marks. Short answers using definitions and properties, and kind of yeah, don't take too much time. Right, so the next question is, and you will always have a question about kind of properties of random variables. Okay, so in this case, you have x, a random variable, which is continuous. Okay, so in general, I'll just give you a property here that we're going to use. If x is a random variable and a random variable with a probability density function f of x, and g of x is a function of x, then the expected value of g of x is equal to the integral, assuming that this is a continuous variable, over all the values of x, of g of x, f of x, dx. Okay, so this is a property for a continuous random variable. And in fact, if that variable was not continuous, the only thing that we would have changed is to, instead of integral, have a summation. Okay, so I can have it like this so that it can cover all cases. Okay, so here in this second part, we have a random variable that is continuous, random variable x with this density function, and we need to find the value of k. So the property that we will use, like the property that we will use to find the value of k, is that when we add all the values of that PDF, it should give us 1. Well, here, because you have a continuous variable, we integrate. Okay, so we have the integral of the f of x dx equals 1. And then substituting, you have k integral from 0 to 1. And I use that integral from 0 to 1 because this is what we were given. Okay, so just pay attention to the support of that function, and then substitute the function itself there and integrate. So that is equal to 1. And when you do that integral, you end up with k over 12 equals to 1, which gives you k equals 12. Okay, so I'm going to skip the actual integration because this is something you can do. It's kind of it's just integration, really. Okay, so we have derived the value of k. Now, in order to compute the variance of 1 over x, now think of 1 over x being a function of x. So this is kind of what I wrote earlier. So you can think of that g of x equals 1 over x. Okay, and now in order to find the variance of kind of any random variable, the property will be to take the expected value of 1 over x squared minus the expected value of 1 over x all squared. Okay, so this is where we're going to use the property that I gave you earlier. So 1 over x is a function of the random variable. So we take that function and multiply it with the PDF, okay, and then integrate. Okay, so we have already calculated k, so we can use that 12 there. And then the function is 1 over x. The PDF is x squared, 1 minus x dx. and doing that integration will give you 2. And then likewise, and I'm just going to sort of copy paste that and just change the terms here. So 1 over x squared, I have an x squared here and x squared there. And again, doing the integration, I mean, you can see here that this guy and this guy will cancel out. So you have a easier integral to do. So that will give you 6. And then just plugging in these results in the original equation that I wrote for the variance earlier on gives you 6 minus 2 squared. Okay, so don't forget the square over there. And that is equal to 2. Okay, so that's a typical question on a continuous random variable. And most likely you're going to have, well, yeah, that's that. Then the next one is about normal distribution. And you will have a question on either a normal distribution of the population or of the sample mean. Okay, so either way, a normal distribution question is very likely to appear in your paper. Okay, so here you start with 2 independent random variables, independent, so you have basically x, normal distribution with mean 1 and 3, which is independent of y, which is also normally distributed with mean 0 and 4. And we need to calculate the probability that x is greater than y. This can be kind of rewritten as the probability of their difference being greater than 0 if we define the difference as x minus y. And that will have a normal distribution because of independence and because you have a linear combination. So let me write it here, that we have linear combination of independent normal random variables. Okay, so due to the independence, so we subtract the means and we add the variances. Okay, so you would have 4 plus 3 equals 7, and then you use that kind of new normal distribution to calculate the probability. So you standardize first 1 minus, or rather 0 minus 1. 0 minus 1 over square root of 7. You calculate the value z greater than the negative of 0.38. Now depends on what type of statistical tables you're given. This is equal to the probability of z less than. So I always draw this graph because it's better to visualize it. So that's z greater than a negative value means that you have this area, okay, which is the same as that area. Okay, so this is less than 0.38. This is the cumulative probability at 0.38. And using the tables, you find it being equal to 0.6480. Okay, so I think this is quite straightforward question. You may get a bit more complicated, but anyway, that's a normal distribution question. The next one is about like the property of estimators. And here is like an open-ended question: explain why we must use both the bias and the variance when we're judging estimators. So when you have this open-ended question, define the variables, or like the parameters rather, that you're using. So let's say theta is a population parameter, and theta hat is the estimate, the estimator of theta. Then the property that we are interested in is the mean square error of theta hat, which is defined as the variance of theta hat plus the bias of theta hat squared. Okay, so this is the definition. So we want to choose. So we choose the estimator with the smallest mean square error. Okay, so the mean square error combines the bias and the variance, and this is why we are using it. And you could, if you wanted to, just to give you kind of a bit of an edge, you can use an example why this is the case. So let me just move that slightly higher. Yeah, so that I can draw an example. So suppose the estimator, the parameter estimator was theta, and you had two estimators. One was one had a small variance, a small bias, let's say theta 1 there, theta 1 hat, and the other had a big variance, a bigger variance, bias, theta 2 hat. Okay, now suppose the one that is closest to theta, in fact, let's make one unbiased. Let's make that theta 1. Theta 1 hat being unbiased. So that means that the expected value of theta 1 hat will be the same as the theta. Okay, so they're kind of on the same spot. While you have the expected value of theta 2 being a bit further away. So one is biased and the other is unbiased. Sorry, I just want to make my graph theta 2 hat. Okay, so you have one unbiased estimator, theta 1 hat. However, assume that this theta 1 hat had a very big variance. Had a very big variance. Okay, while the other one, the theta 2 hat, I'll put it a bit closer. Okay, although it is not unbiased, suppose it has a much smaller variance. Okay, so in this example, you have one unbiased estimator with very big variance and one biased estimator with much smaller variance. So looking at both the bias and the variance of an estimator gives us a better understanding of the property of each one, and then we can decide which one has the smallest mean square error and choose that. Okay, so moving on to a case where we have, what is it? Yeah, so this is another example of from another paper actually about properties of estimators. Okay, so you're given a random variable x that takes three values, 0, 1, and 2. And one single observation is taken, and we would like to estimate the value of alpha, the unknown parameter. Okay, so we're considering two estimators, T1 and T2. Okay, and you need to show that they are both unbiased. Okay, so when we're asking to prove that something is unbiased, then we need to calculate the expected value of T1. Okay, so that is, in this case, it's simply the expected value of x, right? And that we can do using the distribution of x. Now, x takes the value of 0, of 1, and of 2, which means that in that expectation, you have 0 times the probability of 0, which gives you 0, 1 times the probability of 1, which gives you alpha half, plus 2 times the probability of 2, which gives you this. So you basically have a half plus a half equals alpha. So what we say is that T1 unbiased. In order to prove that T2 is unbiased, then we kind of work along the same lines. Applying the properties of the expectation, you have 2/3 and then expected value of x squared. Okay, and likewise, you would have 2/3 of 1 squared times the probability of 1 plus 2 squared, 4 times a over 4, alpha over 4, and that gives you alpha plus alpha half, so 3/2 alpha, and then multiplied gives you alpha. So again, that gives you an unbiased estimator, T2 unbiased. Okay, so this is the first one. And then which of these estimators do you prefer and why? Well, we are going to choose the estimator with the smallest mean square error. Okay, so since both of them are unbiased, so need to calculate the variance of each one. Okay. Okay, so the variance of each one, I mean, I'm going to just write it as variance of T1 is going to be the variance of x. And we can do that because we have the probability distribution of x. And likewise, the variance of, I mean, yeah, so that will always be kind of here you're going to have e of x squared minus e of x all squared. We have already calculated e of x, so we only need one term there. And then the variance of T2 is going to be the variance of, let me write it, variance of 2/3 x squared Okay, so that will be 4/9, the variance of x squared. All right, and then that will be 4/9. The variance of x squared is the expected value of x to the 4 minus the expected value of x squared all squared. Let's kind of let me write this a bit more space here. So you need that guy squared. Okay, so all these terms are straightforward to calculate because they are functions of x. We know the distribution of x, and then you're just kind of simply doing a bit of work there. Some results are feeding into the other, so this term will feed here. So it's really just a couple of terms that you need to calculate. All right, so let's move on to the next question, which is just a probability question. And this type of questions, you need to look at whether the different events or try to identify independent events, whether you are given conditional probabilities. If you're making a selection, think whether it is with or without replacement. Think of whether it is ordered or unordered. So these are kind of the key things to try to identify when you're given such a question. Sometimes you need to draw a kind of decision tree. If that is the case, typically if you have like a Bayes theorem type of question. Okay, so here you're given 10 people seated in a random manner in a row of 10 lecture theater seats. What's the probability that two particular people, A and B, will be seated next to the other? Okay, so if you you can do a bit of a diagram if that helps you. So the fact that A and B sit next to the other means that you have only sort of 9 spaces that you can hold them. All right, so that simple diagram helps you visualize the kind of problem you have. Okay, so and then this. All right, so probability of A next to B is just 9 possible positions, and that will be the favorable outcomes. And the total number of outcomes are 10 choose 2, and that will give you a fifth. And in this method, we have kind of assuming unordered seating. Oops. Unordered. Okay, if we assume that the order matters, then we have to take into account, duplicate, that if you have, let's say, A and B, then that could be BA. Okay, that's like a different outcome. So you have 2 times 9. And then in the denominator, you have 2 times 10 choose 2. And again, that gives you the same outcome, ordered seatings. Okay, so that was one type of question. You may have a different one. So this is from another paper. So typically you're not going to have two probability questions on the same paper. So in a game of two fair dice are thrown. If the sum of the two dice is odd, they are thrown once more. What's the probability that the dice in any final throw of the game is the same? Okay, so here we have a case of kind of different outcomes, like drawing that decision tree is helpful. So we're looking at the kind of the desired outcome is that you have the same number. Okay, so you can define that as, let's say, A, that's your outcome, like that's your event, and you can just call it A to have a nice notation. So the probability of A here, that you have the same outcome when you draw the two dice is 6, and you can see that if you kind of draw that grid of outcomes, 1, 2, let me make it smaller, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So it's kind of this diagonal elements. All right. So that's a 6. And then the next one is having an odd outcome in the first throw. Now, again, if you look at the sum, actually not an odd, the sum is odd. Okay, so this is the sum of the two dice are odd. Okay, so this is what we call it here. That probability is a half. And if that happens, then we throw again, and then the probability of getting the same outcome is a 6, and the probability of a complement is 5, 6. Okay, so yeah, I mean, if you just look at this graph, you have the probability of even sum is the same as the probability of odd sum, and this is a half. Okay, you can verify it by just kind of checking that grid. Okay, so the question is, what's the probability that the two dice have the same number? Okay, so we can break this down into A from first throw plus probability of A on the second throw. Okay, so that is the total probability law. And then from the first throw, that probability is a 6. From the second, it's a half times a 6. So the answer would be a quarter. Okay. Right. So that's another question involving calculating probabilities. So these were typical questions of section A. I've done a few additional, so the marks of section A, I think it's the 40. Maybe I have done a few more. So anyway, so the next questions are about section B, and you will always have a question on joint probability distribution of discrete variables. And this is an example here. You're given X and Y that take values 0 and 1, and you're given the joint probability distribution. Here, that distribution has an unknown value A, and you need to first find that value of A and then answer some more questions. So the properties that any distribution satisfies, and that is true for the joint distribution, is that its values add up to 1, and also its values take like they are between 0 and 1. So in this case, if you add all these values, it gives you 1, but that doesn't help you calculating alpha. Okay, so what you should have is check the other property, that any probability should fall between 0 and 1. Okay, so that's the property. And in this case, that translates into having 1 minus 3 alpha between 0 and 1, and alpha between 0 and 1. Okay, so both of these need to be satisfied. So the first one, if you rearrange and solve for alpha, you have alpha between 0 and a third, and the second one stays the same. And because you want both of them to be satisfied, so if you kind of draw that number line here, it's obvious which one it is, but in other cases, it will be less clear. So you basically have the intersection of this range and this range. Okay, so the intersection of these means that alpha should be between 0 and 1/3. Okay, so that's the first part, 2 marks. And then the next part says that, okay, now take alpha to be a 6th. Okay, and it is, we are allowed to do that because 1/6 is between the range of 0 and a third. Okay, and then the next bit is to calculate the properties of U and V, because you need to then find the mean and also to check whether they are independent. So in order to find the mean of these new variables, U and V, let's find their distribution. Okay, so you have, starting with the marginal distribution. Okay, so the value of U, so the way to do it is to take every combination of X and Y. Okay, so if you have like 0 for X and 0 for Y, then U will be 0. If you have 1 for X and 0 for Y, U will be a half. 0, 1 will give you a half for U, and 1, 1 will give us 0. Okay, so kind of adding up. So let me just make it as, well, in fact, I'll just, okay, so from this, we see that you can write the PDF of U either as a table or as a function, whatever is more convenient. So you have probability of U equals 0 is yeah, so what is that? When is 0 and 0? You have 0 and 0 over, okay, so actually, let me write this for alpha equals a 6th. We have x equals 0, x equals 1, y equals 0, y equals 1. So this is the table. Okay. And then the probability, so I'm going to write it here as alpha equals a sixth. Okay, so that probability becomes a half here, and then a sixth, and a sixth, and a sixth. Okay, so in that case, having 0, 0 is a half, and then 1, 1 is a sixth. So that gives us the probability of u equals 0 as 2/3. And the probability of u equals 1 equals 1/3. Okay, so this is the marginal distribution of u. And of course, these two add up to 1, so there are no other possible values. Okay, so from these, we can also derive the properties. Okay, so from this, you have the expected value of u equals 0 times 2/3 and 1 times 1/3. So that's straightforward equals. Okay, so what have I made a mistake here? Yeah, because that value there is not a 1, it's a half. Yeah, so you can take the value 0 and a half. So then that number is 1/3 times a half, and that's a sixth. Okay, so similarly, okay, similarly, you have kind of all the pairs of x and y's. So for x and y 0, 0, you have v equals 0. Yeah, and then you have 1, 0, v equals 1/3, 0, 1, v equals 1/3, right? And then 1, 1, 1/3. Okay, so that gives us probability of v equals 0. That's a half, and the probability that v equals probability that v equals 1/3 is a half. Okay, and likewise, the expected value of v equals 1/3 times a half equals a sixth. Okay, so we have answered part 2, and then for the last bit, to check if they are independent, what needs to do, so looking at the proper definition of independence, u and v are independent, and then if and only if probability of u comma v is the product of the two marginals. So probability of u times probability of v for all pairs. Okay. Okay, so that's the definition. So that means this if and only if means that if we find at least one pair for which this property does not hold, then u and v are not independent. Okay, so if we start with a pair 0, 0, okay, so let's take the probability of u equals 0 and v equals 0. In which cases does this happen? Well, let's identify this. Okay, so v equals 0 here and u equals 0 there. Okay, so this happens when x equals 0 and y equals 0. Okay, so this is equivalent to x equals 0 and y equals 0. So there is no other case when this can be true. Okay, because for instance here, if u equals 0 there, v is not equal to 0. So this is the only case that both variables are equal to 0. And from that joint distribution, if we go back to that table now, that is the case here. Okay, so that is equal to a half. Okay, so this is the joint probability. Okay, so this is the joint probability of u and v both being equal to 0. How about the marginals? So u equals 0 times the probability of v equals 0. So now we look at the marginal probabilities. So you have this times that. So 2/3 times a half. So 2/3 times a half, and that's equal to 1/3. Okay, so as you can see, these two are not equal, which means that u and v are not independent. Okay, so we found one pair for which that property does not hold. All right, so that concludes the question on the bivariate distribution. Okay. Another question that you will always get is, in fact, let me summarize it here now that you have, have the space. So we have 3 methods of parameter estimation. Okay, 3 methods. What are these? The first one is the method of moments. The second one is the maximum likelihood method, maximum likelihood. And the third is the least squares estimator, least square error or estimator. So this is the method of moments, that's the MLE, and this is the least square estimator or least square error. Okay, so you will have one question from each. Okay, so that is the least square error method. You will be given sort of 2 or 3 equations that they involve an error term and some parameters. And so the steps to follow is to solve for the error term. 1 second. So solve for the error term. Okay, let me give you the steps. Solve for the error terms. Then take the square of the error terms. Then add all the squared error terms, and then minimize the sum of these guys. Okay, so straightforward steps but they involve a bit of math work. Okay, so really the steps here, I mean, I've told you the steps, but I'll just rewrite them here. So epsilon 1 will be y1 minus 2a minus b, and then epsilon 2 will be y2 plus a plus b, and epsilon 3, y3 plus a minus beta. And then, so really, in terms of, we have this guy here, okay, because this is what squaring is. And then the next step will be adding them up. So let me just kind of write it as the sum. Okay, and then the kind of last bit is minimize with respect to A and B, the sum of yi squared from 1 to 3. Okay, so these are the steps. How do we minimize this? We minimize by taking partial derivatives. Okay, so this will be like if I call this summation minimize with respect to AB of that sum of squared errors. Okay, so that sum of squared errors is a function of that A and B, alpha and beta. Then we have the derivative with respect to A of that sum of square errors, setting equal to 0. And same thing with respect to B. And solve that system to find A and B. Okay. All right, so that's exactly what is described in the solutions. We need to minimize. This is the sum of squares of the errors that I gave earlier. So I've just written it as that above. And in order to minimize this, we need to differentiate with respect to A and set it equal to 0. And then differentiating it with respect to B, setting it equal to 0, and then solve the system. And when you find the answer, you need to put that hat on the top of the sort of solution. And then once you have done that, you need to prove, I mean, perhaps by solving that solution, you should also get an answer for A, and then that would be like A hat. And then you need to prove that they are unbiased. Now, if you have done the calculation correctly, then you will get an unbiased estimator. Okay, so the way to prove that it is unbiased is to basically take the expected value of that expression. Okay, that expression will involve the functions of yi. So then you replace the functions of yi's, and you need to keep in mind that these error terms, okay, the error terms have 0 mean, and the error terms have constant variance sigma squared. Okay, so that's how you kind of prove that last bit. So just so I'm just writing it here so to have it in mind, because what you need to remember is that the properties of the variance. So I'm just going to do the variance bit just to demonstrate it. So the variance of the beta hat will be the variance of like y1 minus 2y2 plus 4y3 over 7. Okay, so the property of the variance means that you square the scalars. So that will mean that you have the variance of y1 plus 2 squared. So that would be 4 variance of y2 plus 16 variance of y3 over 7 squared, 49. Okay. And again, if you substitute in y1, what over here, if we substitute, what was the expression for y1? All the way up here, it was 2a plus 2 alpha plus beta plus the error term, 2 alpha 2 alpha plus beta plus the error term 1. Then, well, the only random term here is the error, okay? The alpha and the beta are not random variables. So if you take the variance of a non-random term, that is equal to 0. So we end up with the variance of the error term 1 plus 4 times the variance of the error term 2 plus 16 times the variance of the error term 3 over 7. Now, all of these error terms have the same variance. So we end up with 20, not 7, 7 squared, 49. Okay, so we end up with 21 sigma squared over 49. And so that's a 3, yeah, 7, 7, 3/7 sigma squared. Okay, so that's the first method, least square estimators. Okay, least square estimators. It's not, the difficulty here is to basically solve the system. Okay, solve the system of equations. Other than that, and just remember to put a hat whenever you estimate a parameter. I'm going to do the other two methods in a minute, but you will also have a question on ANOVA, analysis of variance. So let's do that now. So for the ANOVA, you need to fill the table of like this ANOVA table using the information provided. So over here you have 3 major television stations, networks. So 3 minus 1 at 2. And you have 4 major cities. So 4 minus 1, 3. And then, so that will give you 3 times 2, 6 for the degrees of freedom of the error. And then 11 is the total. In order to calculate, well, the sum of squares here, sum of squares for the city, is going to be based on, you're given the mean square, so it's going to be that mean square times the degrees of freedom. So that will be 3 times 1.95, that is 5.85. For the network, you are given the sums, or not the sums, the means of the 3 different networks. Okay, so from these 3 means, you're going to calculate the overall mean, x bar, which is 2135 plus 1728 plus 2018 over 3. Okay, so that will give you the 19.60. And then you're going to need to calculate the sum of squares for the networks. Okay, sum of squares of the networks is going to be the square differences between the average of the network and the overall average. So we are having 21 minus 35 minus 1960 squared. And likewise for the second network squared and for the third network. And then this term, all of this needs to be multiplied by the number of cities. Okay, so the number of cities is 4. So multiplying this by 4 will give you the 13. Okay, so that will be the sum of squares for the network, 35, 13. And then the mean square for the city, or rather mean square of the network, is going to be the sum of squares of the network divided by 2. So how much is that? 17.57. The sum of squares of the error, sometimes the error, we call it residual, is the total sum of squares minus the sum of squares of the city minus the sum of squares of the network. So plugging in the numbers will give you 1054. So we can write that 1054 there, which is the sum of square of the errors. And finally, the mean square errors is going to be, again, mean square errors. All the mean squares are basically the sum of squares divided by the degrees of freedom. So giving that 1.76. The F values, for the F values, we always, the denominator is always the mean square of the error. Okay, always the denominator. So the F value for the city is the mean square of the city. And if you duplicate that and just replace city with network, will give you the F value, F statistic value. So this will be, what's the numbers? So the denominator will be the 1.76, and the numerator for the city is 1.95, while for the network it's 17.57. And just to do that, yeah, okay. So we have 1.11 and 9.98. Okay, so let's add those into the table. 1.11 for the city and 9.98 for the network. And the distribution, the sampling distribution of those is you're using the degrees of freedom. The first degree of freedom will be the corresponding grouping, so that will be the city, and the second is always the error. And then the question was about 5% significance level. Now, this type of test is always one-sided tests, always. Okay, so we keep the significance level without splitting it, and that will be an F distribution with degrees 2, 2,6, and again 0.05. Okay, and if you look at the statistical tables, for the second one, which is the question, that is equal to 5.14. Now, in order to conduct the test, we need to also write the hypothesis. Okay, so the null hypothesis, since we're comparing now networks, okay, so how many networks do we have? A, B, C. Yeah, so the null hypothesis is that the mean of A is equal to the mean of B is equal to the mean of C versus, we can write that using words as well. Like this corresponds to all the population means of all population means of all networks are equal versus the alternative is that at least one mean network, at least one network has different mean. And we're always talking about the population mean, of course. Okay, so stating first the hypothesis. So we have performed the test, we have derived the test statistic value. In this case, it's 9.98. We know the distribution. So just to kind of draw that very simple graph, as I said, always one-sided. So that will be an F distribution, 2,6. And the threshold value, so that was the test statistic value, 9.98 is your F value for the network. And the threshold, the F of 260.05 is, as we said, 5.14. So we have we reject H0, okay? And then we need to write the conclusion, okay? So the conclusion is there is enough evidence. Let me write the evidence. There is enough evidence to suggest that the networks that there is a difference in the networks. Okay, so okay, so that's that really. So this is the question on ANOVA, okay? Analysis of variance, and we're moving to the next exercise, which is the other method of estimating parameters, population parameters. This is the method of moments. So during the method of moments, you basically have equations where we are putting the population moment defined as expected value of x to the k equals to the sample moment. Okay, and the sample moment is the sum across all the sample values of xi's to the k. Okay, so this is the basic idea of the method of moment, and you create as many equations as the number of parameters you need to estimate. So in here, you're given a uniform distribution 0 theta, one unknown parameter. Use the method of moment to estimate the theta. So first of all, you need so we need the distribution. So that distribution is equal to, of the uniform, is 1 over theta, where x is between 0 and theta, and 0 otherwise. So using that probability distribution, we are going to calculate the expected value, and that is 0 to theta. So make sure that you have theta there because that's the domain. Okay. And that will give you, if you do all the work, theta over 2. Okay. Now this is the first population moment. And then the first sample moment is simply sort of, for the sample moment, we always take the first sample moment, we always take the sample mean. Okay, so this is the first sample moment. And what we do is to create that equation. So let me just make that. Okay, so the equation we create is E of x is equal to x bar. Theta over 2 is equal to x bar. And so theta, write it as theta hat is equal to x bar over 2. Okay, which is, or rather, sorry, we have 2 theta, 2x bar. Okay, which means that you have like theta hat equals 2 times the sum of xi's over n. Okay, so this is the method of moment estimator. Now, if you're given a small sample, in this case, these values, what you do is kind of, if you use it, you end up with theta hat equals 2 times the 0.3 plus 9.7 plus 2.6 divided by 3. And that gives you a number 8.4. The problem with that is that this 8.4 is smaller than one of the observations. So x2 is equal to 9.7. So this is a contradiction. Because if that uniform is defined between 0 and 8.4, we cannot have an x2 which is 9.7. We cannot have an observation which is outside that range. Okay, so this is a contradiction. The reason why we get that is because we have a very small sample, and alternatively, if in order to basically correct for that, we need a bigger sample, and that will asymptotically we will be okay if the sample was big. However, we could use the maximum likelihood method. So let me take you through that. Based on maximum likelihood method, we get the following. We get the joint distribution x1, xn equals to the likelihood due to independence. So let me write, because the xi's are independent, due to independence. That product from 1 to n of the f of xi's, suppose, yeah, and then this is equal to 1 over theta times 1 over theta, so that will be 1 over theta to the n. Okay, so this is your likelihood function. So let me rewrite it here. Okay, I can write it over there as let me just correct that notation a bit. Okay, so this is your likelihood function. Okay, so we cannot use that other method of differentiating, setting it equal to 0, because like if we were to do that, we would not be able to solve it. So instead, what we are using is try to understand how this function behaves. Okay, so we can draw that. We can draw that function, that likelihood function, as a function of theta here. So you have L of theta. So this is, since theta is in the denominator, this is an decreasing function of theta, okay? This is a decrease. So basically what we say is that L of theta is a decreasing function of theta. Okay, why is that? Because theta is in the denominator, so the bigger the denominator, the smaller the fraction. However, like if we have the observations have to be smaller than theta, okay? So if we have the sample maximum here, okay? So this is, let me write it as the maximum of the sample x1, x2, xn, okay? This is the sample maximum. Then the value of theta has to be bigger than the sample maximum, okay? Because if it is smaller, then by definition, okay, what's the definition here? That PDF will be 0, okay? So if you have basically an observation which is bigger than theta, which is equivalent to saying the theta is smaller than that observation, the PDF will give you 0, okay? Which means that you have that 0, 0, 0 kind of case. So if theta is less than any of the observations, then that likelihood function is equal to 0. Then it becomes, that likelihood becomes 1 over x of the maximum to the n at this point. And then it is a decreasing function of theta. Okay, so the maximum, it is achieved at the maximum of this likelihood is achieved at the sample maximum. And so that will be the MLE estimator. Okay, so this is the case where we basically have a likelihood function, or in fact, the reason why we end up with this type of method is because theta, the unknown parameter, is in the support of that distribution. Okay, so we have theta here. It is involved in the support as well. Okay, so this is the case where we have a uniform distribution and we calculate both the method of moment estimator and the maximum likelihood estimator. Okay, another case, another example of maximum likelihood estimator is like this is the more conventional. All right, you're given a distribution where the support does not have the parameter you're trying to estimate. And so you need to derive the estimator for lambda here. So you should always start by stating due to independence, due to independence. And this is okay, due to independence, you have the joint distribution x1 to xn given lambda is equal to the product of the terms of the f of xi's, and this is equal to the likelihood function. So we can have that the joint distribution is considered as a function of the data, while the likelihood is considered as a function of the parameter. So that is equal to the product from 1 to n of lambda to the 2xi e to the minus lambda squared over xi factorial. Okay, so that's the likelihood function. So how does this becomes if you kind of expand that, you have lambda to the 2x1 times e to the minus lambda squared over x1 factorial. And then you have similar terms for each observation, e to the minus lambda squared over xn factorial, and that simplifies to lambda to the 2 sum of xi's e to the minus n times lambda squared over the product of xi's factorial. Okay, so right, so this is your likelihood function. Okay, so we can just write it here just to have it. And then how can we find the lambda that minimize this function? Then the next step is to take logs, take the log of the likelihood function. Okay, so that yeah, so this is now L of small lambda, which is the log of the likelihood, and the property of the log is that it turns the product into summation. So we're going to have 2 times the sum of xi's from 1 to n times the log of lambda minus n lambda squared minus, and here you have the log of the product of this xi's factorial. Okay, then the next step is to differentiate with respect to lambda. Okay, differentiate with respect to lambda and set equal to 0. Okay, so then you have the derivative of this with respect to lambda equals to 0. So the third term does not have any lambda, so it will be cancelled out. The derivative of the log of lambda is 1 over lambda. So you have 2 times the sum of xi's from 1 to n over lambda minus 2 times n lambda equals 0. So you basically have that. Okay, so this is, let's put the hat over there. The 2's cancel out as well. So if you kind of rearrange for lambda, you have lambda hat squared is equal to the sum of xi's over n. So lambda hat is equal to the square root of x bar. Okay, and this is your maximum likelihood estimator. Okay, so then for the next part, which is to state, let me copy that, copy, so we have that theta equals lambda squared, so it's a function of the parameter. Now you need to say that due to the invariance principle, we have the same function that we applied to the parameter, we applied to the estimator. So theta hat is equal to lambda hat cubed, and that will be lambda hat was the square root of the x bar. So that will be cubed, and that's another way of saying x bar is to the power of 3/2. Okay. So that completes the question on the maximum likelihood estimation. In fact, we have done 2 questions on the maximum likelihood. One where the answer is derived by differentiating the likelihood function, like first taking the log and then differentiating. And the other is by looking at the shape of that function and kind of finding the peak using this graph. All right. So then the last type of question you're going to have is find sort of this is based on how we generate all the distributions really from the normal. Okay, so I'll take you through the steps as we solve these questions. So we start with xi's here being normally distributed. In fact, they are IID. Okay, so independent and identically distributed with normal mean 0 and variance 3. So looking at the first question, you have squared functions of these variables. Now, the steps we need to follow is first to standardize each one of these xi variables, because these are the building blocks or the standard normal distributions. So by subtracting the mean and dividing by the standard deviation, which is basically xi over square root of 3, we end up with a standard normal chi-square. Then the standard normal, then when you square this, you end up with a chi-square with 1 degree of freedom. And then when you are adding independent chi-squares, you're just adding the degrees of freedom. So you end up with x1 squared plus x2 squared plus x3 squared plus x4 squared over 3. Okay, so that now becomes a chi-square with 4 degrees of freedom. Okay, so these are the steps: standard normal, square of the standard normal, and then adding independent chi-squares. Okay, so then now that we have created this chi-square distribution, then we look at the question we have. So the question we have is to calculate this probability. And the way to do this, to calculate this probability, is compare it to the random variable that we have created. Yeah, we have created this random variable, and we need to make this expression look like that. Okay, so these are the kind of steps. So the way to kind of make the two the same is to divide by 3 both sides of that inequality. Okay, so by dividing both sides by 3, we have now created a chi-square 4, and we want that to be less than k over 3, and that's to be equal to 0.99. All right, so we look at the tables. So let me just move that here. We look at the tables of the chi-square distribution with 4 degrees of freedom. Okay, so this is the chi-square 4. Since we're looking at a 99%, we know that it's kind of, we're looking at the cumulative. So all of these should be equal to 0.99. Okay, so on the statistical tables, the value that gives you a cumulative of 0.99 is 13.277. Okay, which means that in order to find k, we just need to say that k over 3 is equal to 13.277 and solve for k. So k becomes 39,831. Okay, so that was the first of these 3 parts. Let's now for the second we need to first rearrange that expression so that all the x variables are on the same side. Okay, so let me quickly copy that over here. Okay, so this is part 2 now. So first thing is to rearrange and make that a probability of x1 squared plus x2 squared over x3 squared plus x4 squared less than 99. So find that probability. Okay, so that reminds that this expression, because you have squared terms both in the numerator and the denominator, suggests that we should try to create an F distribution. And the way to create the F distribution is to take ratio of chi-squares. So first need to create chi-squares. So following exactly the same steps as in part one. So you have first the standard normal, then the square of that standard normal makes it a chi-square of 1 degree of freedom. And then you take independent sums. Okay, so you end up with variable v, let's say, which is x1 squared plus x2 squared over 3. And that has a chi-square distribution with 2 degrees of freedom. And if you take different terms like x3 squared plus x4 squared over 3, that will also be a chi-square with 2 degrees of freedom. And you also have that v and w are independent because they don't have common terms and because the xi's are independent, which means that if then we take the ratio of chi-square variables scaled by their degrees of freedom, then we end up with an F distribution with degrees of freedom, the 2 degrees of freedom of the X and chi-squares. Okay, so we end up with, let me write this, duplicate this guy here divided by 2 over, okay, so that was the V, over it's 1 divided by 2. Okay, now there are obviously some simplifications there. So the end result is x1 squared plus x2 squared over x3 squared plus x4 squared following the f2, 2. Okay, so that means that we can use the table straight away. And basically that top probability is just the probability of the f2, 2 being less than 99. Okay, and looking at the tables, it's easy to find it. And now finally, let's move to the last part, which is that third question. Copy, and let's put it here. Let me, okay. So in this last exercise, you need to again first rearrange the terms so that all the x's are on the same side. So you have the probability of x1 over square root of x2 squared plus x3 squared, okay, being less than k. All right, so this expression here reminds us of a t-distribution, but it's not yet a t-distribution. We need to create that t-distribution. So again, we start with a standard normal. Okay, so that's a standard normal. We also need a chi-square in the denominator. Okay, so using the results of the previous, well, in this question you have, okay, we have, just following the same method as before, we have x2 squared plus x3 squared over 3. This is a chi-square distribution with 2 degrees of freedom. And let's call that variable like v. And let's call that variable z. Okay. So v and z are independent because they don't have any common xi terms. And So if we take the ratio of a standard normal over the square root of a chi-square scaled by its degrees of freedom, we create a t-distribution with same degrees of freedom as the chi-square. And so just to kind of put that into place for this case, we have z being x1 over square root of 3, and the v is, let's take the v here. This is the v, and we need to scale it by its degrees of freedom, which is a 2, and we need to take a square root of that. Okay, so this has a t-distribution. How does this simplify? Well, that square root of 3 with that square root of 3 cancel out. This square root of 2 is in the denominator, which means that if you rearrange it, it becomes in the kind of in the numerator. So we end up with a square root of 2 times x1 over square root of x2 squared plus x3 squared, following a t-distribution with 2 degrees of freedom. Okay, so that's the kind of the prep work in order to be able to find the random variable. Okay, so then we'll look at the question we need to answer. Okay, so the question, so basically we are comparing this term with this term. Okay, and how different are they? So the difference between these two is that it's basically this guy here, the square root of 2. Okay, so that's the difference, which means that if I take that probability, yeah, if I take that, well, actually, I can do it straight away there. The way to find that probability is to multiply both sides by the same term. Okay, and now this is a this is a t distribution with 2 degrees of freedom. And so we need to look at that statistical tables. Okay, so the t is, as we know, symmetric, and we need a probability that is like a cumulative probability that is equal to 0.01, which means that it's on the left-hand side. Okay, so that area here will be the 0.01. The way to find it is, depending on what table you have, to look at the symmetric of that. Okay, so the symmetric value will be kind of here. Okay, so that will be 0.01. So, and then flip it. Okay, so the value that gives you a cumulative of 1% is negative 6.965. Okay, and this is equal to the value of square root of 2 times k. All right, which means that negative 6.965 is equal to square root of 2k. Solving for k gives you negative 4.925, and that's the answer. Okay, so yeah, that completes the third part of this exercise, where we have created a t-distribution starting with normals. Okay, so thanks everyone for attending this or watching this webinar. Good luck with your exams and hope to see you in one of my other webinars. Take care. Bye-bye, everyone.